Hey everyone, ever been in the middle of a massive download, like for a new game or a huge software update, and suddenly your Wi-Fi cuts out? The panic sets in, right? You think, oh no, I have to start all over again. But then, a few minutes later, the internet comes back, and like magic, the download picks right up where it left off. Have you ever wondered how that's even possible? What's the secret sauce that makes resumable downloads? And so many other things we take for granted on the internet actually work? It's not magic, but it's something just as cool. Today, we're diving deep into the unsung hero of the internet, the transport layer, and specifically its most famous protocol, TCP. So let's start with the big picture. When you send or receive data online, whether it's an email, a video, or that massive game file, your data goes on a journey. This journey is managed by different layers of protocols, kind of like a team of specialists, each doing their part. We've talked about some of these before, but today we're focusing on the transport layer. Its main job is, well, transport. It is responsible for getting data from one application on your computer to another application on a server somewhere else in the world. It's the digital postal service of the internet. Now, this postal service has two main ways of delivering things. One is fast and furious, but a bit careless. We'll talk about that one another time. The other, the one we care about today, is all about reliability. This is where the Transmission Control Protocol, or TCP, comes in. TCP is the gold standard for reliable data transmission. Think of it as the ultra-dependable premium courier service for your data. When you absolutely, positively need every single piece of your data to arrive in the correct order, and without any corruption, you use TCP. This is why it's used for things like file downloads, web browsing, and email. You wouldn't want half an email or a web page with random chunks missing, would you? To understand how TCP achieves this amazing reliability, let's use an analogy. Imagine you need to move the entire contents of a huge warehouse from one city to another. The road between the cities is bumpy, unpredictable, and sometimes parts of it just disappear. This unreliable road is our internet. The internet, by its very nature, is an unreliable network. Packets of data can get lost, duplicated, or arrive out of order. It's organized chaos. So how do you move your precious cargo safely through this chaos? You wouldn't just throw everything onto one giant truck and hope for the best. That's a recipe for disaster. Instead, you'd hire a professional logistics company. This logistics company is our TCP. The first thing this company does is break down your massive warehouse inventory into smaller, manageable boxes. This is called packetizing or segmentation. TCP takes the big stream of data from your application and chops it up into smaller pieces called segments. But just having a bunch of identical boxes isn't enough. If they arrive out of order, how would you know how to reassemble your inventory? The logistics company is smart. On each box, they write a unique sequence number. Box 1, Box 2, Box 3, and so on. TCP does the exact same thing. It adds a sequence number to each data segment. This way, even if the segments take different routes and arrive jumbled up, the receiving end knows the correct order to put them back together. It can look at the numbers and say, okay, segment 5 goes here, segment 6 goes there. Now for the most important part, ensuring every single box actually arrives. Our logistics company doesn't just send the trucks and hope for the best. They have a system. For every single box they send, they require a signed receipt from the destination. This receipt is their confirmation that the box arrived safely. In the world of TCP, this signed receipt is called an acknowledgement, or a CK for short. Here's how it works. Your computer sends a TCP segment, let's say with sequence number 1. The server on the other end receives it. If everything looks good, the server sends back an ACK packet that basically says, "Got segment 1, thanks. I'm now expecting segment 2, but what happens if a box gets lost on that bumpy road? What if a truck falls into a pothole and disappears?" Our logistics company has a rule. After sending a box, they start a timer. If they don't receive a signed receipt and a CK before that timer runs out, they assume the box is lost. They don't just shrug and move on. They grab a copy of what was in that box because they cleverly kept a copy and they send it again. This is retransmission. TCP does precisely this. When it sends a segment, it starts a retransmission timer. If it doesn't get in a CK for that segment back in time, it assumes the segment was lost in the digital void and automatically sends it again. It will keep doing this until it finally gets that acknowledgement. This simple but powerful mechanism of acknowledgements and retransmissions is the absolute core of what makes TCP so reliable. So let's put it all together. The fundamental magic of TCP is this. It creates the illusion of a perfectly reliable, dedicated connection over a fundamentally unreliable and chaotic network. It simulates a clean, direct pipeline where no data is ever lost or jumbled. And it does this through a beautiful combination of 4 key mechanisms. 1. Chopping data into smaller packets or segments. 2. Adding sequence numbers to each packet so they can be reordered correctly. 3. Requiring an acknowledgement for every packet received. And 4. Automatically retransmitting any packet that gets lost and doesn't receive an acknowledgement in time. Packetize, number, acknowledge, retransmit. That's the mantra of reliable transmission. It's this constant back and forth chatter of here's data, and got it. Here's the next piece. Got that one too. Wait, I didn't get an ACK for number 47. Let me send it again. This conversation ensures that the stream of data is reassembled perfectly on the other side, exactly as it was sent. This is how your download can pause and resume. When your connection drops, the server stops getting ACKs from you. It waits, retransmitting a few times. When your connection comes back, your computer can send an ACK for the last piece it successfully received. And the server knows exactly where to pick up, sending the next segment in the sequence. No need to start from scratch. This system is incredibly robust. It handles network congestion by adjusting the sending rate. It manages the flow of data so a fast sender doesn't overwhelm a slow receiver, and it ensures data integrity. It's a masterpiece of network engineering that has been the bedrock of the internet for decades. Every time you browse a website, send an email, or download a file, you are using this intricate dance of packets, sequence numbers, and acknowledgements. It's a complete, reliable system for getting data from point A to point B, but this brings up a fascinating new question. Okay, the data has arrived safely at the destination computer. It's all been reassembled in the correct order, thanks to TCP. But now what? A modern computer is running dozens of applications at once. You've got your web browser open, your email client, a game, a chat app. How does the data, this perfectly delivered package, know which specific application it's for? How does it know to go to the web browser and not the game? That, my friends, is the next piece of the puzzle, and it involves something called ports. We figured out the reliability, but now we need to figure out the addressing within the computer itself. It's like our logistics company has successfully delivered the entire warehouse of goods to the correct building address, but now they need to know which department inside that massive building gets which box. We'll explore that very topic in our next video. Thanks so much for watching and getting nerdy with me about the protocols that make our digital world turn. If you enjoyed this and want to see more, make sure to hit that subscribe button and ring the bell so you don't miss our next deep dive. See you in the next one.